Good morning, class. We are looking at chapter 3, polynomial and rational functions. Here's section 3.3, dividing and real zeros of polynomial functions. So we covered power functions, polynomial functions, and graphs. We're going to look at dividing real and real zeros of polynomial functions. The following sections are complex zeros of polynomial functions, rational functions, and inverse and radical functions. The objectives are use the remainder and factor theorem, use Descartes' rule of signs to determine the number of positive and negative real zeros of a polynomial function, use the rational zeros theorem to list the potential rational zeros of polynomial functions, find the real zeros of a polynomial function, solve polynomial equations, use the theorem, and bounds on zeros, use the intermediate value theorem. So here's the summary of polynomials that we have covered. Polynomial functions are in the form of f of x equals a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 plus all the way to a sub 1 x and a sub 0. Here's the leading term and here's the constant. A sub n can't be 0, so we can claim it's of degree n. N is a whole number. That means 0, 1, 2 to infinity. The domain is all real numbers, negative to positive infinity. Couple of simple examples. A polynomial of degree 1, y or p of x is mx plus b. It's a linear function. Polynomial of degree 2, p of x is ax squared plus bx plus c. It's a quadratic function. And as you recall, the vertex is located at minus b over 2a, and you plug in to get f of minus b over 2. What else? The degree of the polynomial function is n. Graph is smooth and continuous. Maximum number of turning points would be n minus 1. In essence, turning points or extremo, max and min. At a zero of even multiplicity, the graph of f of x touches the x-axis. It can't cross the x-axis. At a zero of odd multiplicity, the graph of f of x crosses the x-axis. Between zeros, the graph of f of x is either above or below the x-axis. End behavior. For large values of x, the graph of f of x behaves like the graph of its leading term. So it's called the leading term, everybody. And a sub n is called the leading coefficient. Leading coefficient. So one more time. The first term, if we put it in descending order, is called the leading term. Its coefficient is called the leading coefficient. And in the long run, as far as the concept of end behavior, it will look like that. Section 3.3, dividing and real zeros of polynomial functions. N of x divided by d of x, it gives you q of x, which is the result, the quotient, and then the remainder, okay, r of x over d of x. So when you divide, this is what you end up with. This is the polynomial, which is the dividend. This is the divisor. This is the quotient. This is the remainder. This is the remainder. Division algorithm for polynomials, d of n of x over d of x. Let n and d be two polynomials with the degree of d of x greater than 0 and less than the degree of n of x. Then there exists unique polynomial q of x and r of x such that n of x over d of x is q of x plus r of x over d of x. Or you can do the cross product. N of x is q of x times d of x plus r of x. Dividend is the product of quotient and divisor plus the remainder. Just as you would numbers, where either r of x is 0 or the degree of r of x is less than the degree of the divisor d of x. Remainder theorem. If f of x, a polynomial, is divided by x minus c, then f of c is the remainder. So f of x divided by x minus c, remainder is equal to f of c. Factor theorem. If f of x, a polynomial, is divided by x minus c, and f of c is 0, then x minus c is a factor of f of x over x minus c. That means r, the remainder, is 0. So the remainder theorem says if you divide f of x by x minus c, the remainder is f of c. And factor theorem says when you do that, it is still f of c, but it ends up being 0. Divide 3x cubed minus 2x plus 5 by x minus 3. So let's see how this thing works. So you are dividing 3x cubed minus 2x plus 5. Because the second degree term is missing, you either put 0x squared or you give it some space. If you don't want to write that, either way is fine. And then you are dividing by the divisor x minus 2. So what happens is that you do an approximation by dividing the first term of the dividend 3x cubed by the first term of the divisor. This is just like dividing numbers. If you, for example, look at, let's say, 279 divided by 8. The process is guesstimating. By that, we mean you start with the first one. Can I divide 2 by 9? No. 27 by 9. Let's actually make it more interesting. I don't want it to be divisible by that. So let's make it 289. And so you divide 2 by 9, doesn't work. You go with the second one and you guesstimate by dividing 28 by 9. That's exactly what we are doing by picking the first divided by the first term of the dividend by the divisor. We are guesstimating. With that being the case, we get roughly 3. Okay, over here we got 3x squared. So then what happens is that we multiply these two, we get 27. So we are going to do the same thing here. We're going to multiply 3x squared by x minus 3. We get 3x cubed minus 9x squared. Then we subtract and we get 1. And that's exactly what happens here. I hope you see the similarities. What happens next? Let me use a different color. We bring this one down. And now we divide 19 by 9. So over here, okay, we bring down the next term, which is negative 2x. So divide 19 by 9, you get 2, and then you multiply by it, you get 18. 1, notice 1 is smaller than 9, and we say we are done. So that means we got the quotient, we got the remainder, and so we are going to continue in the same manner over here. We are going to divide 9x squared by x. We get 9x. And now we're going to multiply by it. Remember, we got 2, we multiplied by 9. When we multiply that, 9x by x is 9x squared times negative 3 is negative 27x. We did here, and we subtracted 18 from 19. So we're going to subtract this one from this one. So when we subtract, I want to make sure we understand. So we are subtracting this, right? So you can say this is negative. They cancel each other. This is positive, and we get 25x. And you bring the last one right down. Now, again, you continue by dividing 25x by x. You get 25, and you put it here. And now multiply it by that. You get 25x minus 75. And now you subtract. Subtract meaning you can say this is negative, this is positive. They cancel each other. And that gives us 80. So this is the quotient. This is the remainder. Now I want to look at the number. Going back to the number, I can say the answer. So if I divide, let me just write it here. If I divide 289 by 8, I can say the answer is the quotient plus the remainder over the divisor. That's one way to say it. Okay. Let me, actually I need to erase, so 289. So let's see if we can somehow keep this one, 289 divided by 8. I need this space, so let's do that, everybody. So I'm going to write what we had with the numbers 289 we divided by 9, and we had 32 plus 1 over 8. So I hope you can see that we are doing exactly the same thing, but two polynomials. Dividend, divisor, remainder, divisor. Also, second method, let's use a different color. So I'm going to call it number 1. And now number 2, I can write it as follows. 289 is the product of the divisor and the quotient plus the remainder. Over here, we could write 3x cubed minus 2x plus 5 is equal to the product of the divisor x minus 3 and the quotient 3x squared plus 9x plus 25 plus the remainder. So this is 1, this is 2. There are two different ways of writing it. So if we know long division of numbers, we know long division of polynomials. They are identical. Let's move on by looking at a couple more examples. So if you look at this one and it's been done, again, this is from the previous page, okay? We can drop the variable x or x squared and for example, instead of x, we would write 1. This is 1. Instead of 3x cubed, we would write 3. It looks like that. Now, I want to discuss synthetic division. So if I want synthetic division, I use this part. And it's important to know if you're dividing by x minus 3, you put 3 here. If you're dividing by x plus 3, you put negative 3 here. You drop the first one, you multiply these two, becomes 9, you add these two. And that gives those numbers. However, with a different sign, because this has a negative, this doesn't. And these are the numbers that you find here. When you end up with the numbers, 3 means 3x squared, 9 means 9x, 25 means just 25, and 80 means 80 over x minus 3. This abbreviated form of long division is called synthetic division. Okay, everybody? Synthetic division. Let's do long division quickly. We are going to divide the first one by the first one. Results in 3x. We're going to multiply the 3x and we get 6x squared plus 9x. We are going to subtract, so I'm going to change the sign to negative, These two cancel each other. And we get minus 4x. And we, of course, bring down negative 10. We are going to divide negative 4x again by 2x. And that gives us negative 2. We are going to multiply the negative 2 and we get minus 4x minus 6. We are going to subtract. To subtract, we can change the sign and add. We get negative 4 and we are done. Meaning, the answer to this is the quotient 3x minus 2 and the remainder minus 4 over the divisor 2x plus 3. Now, this one, you can write it in this fashion or just put this here in negative sign. Either way makes no difference. We'll do the same thing here. We start with the first or the leading term divided by leading term, we get 5x. We're going to multiply 5x. By the way, you don't have to put that if you know what you're doing. What do I mean by that? I want to be clear on that. Check this out. When you multiply these two, you get 5x cubed. When you multiply these two, you get 5x. So you line up 5x under 7x because they can be added up, okay? So you don't put it here. Of course, we are subtract. Therefore, we are going to say this is minus. They cancel each other. This makes no difference. You still minus, you get minus 4x squared. This becomes minus with positive 7x becomes 2x. And of course, you bring down negative 2. Now you divide this one by this one, and you get negative 4. You multiply the negative 4, you get negative 4 x squared minus 4. It doesn't matter you write this or not. Just make sure you line them up accordingly. Now, since you are going to subtract the second line from the top line, you are going to change the sign and add them up. This gives you what? 2x plus 2. Now, how do you know you have to stop? The degree of the divisor is 2. The degree of the remainder is 1. If the degree is less, you're done. So the answer is 5x minus 4 plus the remainder, 2x plus 2, over the divisor, x squared plus 1, and you're done. Long division. Use the remainder and factor there. Find the remainder if f of x is x squared plus 3x squared plus 2x minus 1. If this is divided by x plus 2, x minus 1. Let's start with this one. According to the remainder theorem, if you're dividing by x minus c, you have to evaluate f of c. So if I'm dividing by x plus 2, I have to evaluate f of negative 2. So be careful with that, okay? So take a look at this one. So that means I'm going to put negative 2 here and say negative 2 cubed plus 3 times negative 2 squared plus 2 times negative 2 minus 1. That's how we do that. So this is negative 8. This is 4. This is minus 4. This is minus 1. I hope you see that they cancel each other. And so we end up with negative 1. So the remainder is negative 1. For this one, we are going to evaluate f of 1. So just plug in 1. You get 1 cubed plus 3 times 1 squared plus 2 times 1 minus 1. So this is 1. This is 1 times 3 is 3 and 2. 5 and 1. I hope you see 1 plus 3, 4 and 2, 6 minus 1, 5. So it's simple calculation. Use the factor theorem to determine whether the function f of x equals minus 2x cubed minus x squared plus 4x plus 3 has the factor x plus 1, x minus 1. Which means for this one, we have to evaluate f of negative 1. F of negative 1 means negative 2 times negative 1 cubed minus negative 1 squared plus 4 times negative 1 plus 3. This is negative 1 times negative 2 becomes positive 2. This is positive 1, so it becomes minus 1, minus 4, plus 3. They add up to 0. Therefore, the answer is yes. Dividing by x minus 1. If you want to see if it's a factor, you have to evaluate that f of positive 1. So plug in here minus 2, 1 cubed, minus 1 squared, plus 4 times 1, plus 3. So we are going to plug in positive 1 here. And I chose this question on purpose. I want you to see for this one, you choose negative 1. For this one, you choose positive 1 because of what it says here. If it's x minus c, you evaluate f of c. Be very careful with that. Now, this is 1 with the negative 2. Becomes negative 2. This is 1, but negative is outside. You get positive 4. The answer is no. It's not a factor. The only time it becomes a factor, okay, if the remainder is 0. Remainder is 0 here, but not here. Therefore, this is a factor. This is not. Example 3, use the remainder theorem and synthetic division to find P of negative 2. Before we tackle this, if they said remainder theorem, it's a lot easier to just evaluate P of negative 2. I want you to know that, okay? However, just for practice, we are doing synthetic division. So if they ask you whether this polynomial is divisible by x plus 2. When we say P of negative 2, everybody, that means we are looking at divisor of x plus 2. We are dividing by x plus 2. And the faster way is to evaluate P of negative 2. It's a lot faster than the synthetic division, but you really should know both. So the way we do that is very simple, okay? We put these numbers negative 1, positive 3, let me just negative 1, positive 3, minus 4, and negative 5. So, and we notice what's missing. This is of degree 4, this is of degree 2. So degree 3 is missing. You must put a 0. If you don't do that for long division, you could make it work. But if you don't do that for synthetic division, you can't make it work. It will be wrong. So one more time. Degree 4, negative 1. Degree 3, missing 0. Degree 2, 3. Degree 1, negative 4. Constant, negative 5. And you put the negative 2 here. You drop this number just the way it is. You don't have to do anything. Just drop. Then you multiply it by negative 2. You multiply this by negative 2. You get positive 2. And you add up these 2. You continue. You multiply this one again by negative 2. And you get negative 4. You add up these 2. You get negative 1. You multiply this one by negative 2 and you put it here. Negative 1 times negative 2. Positive 2. With negative 4, they add up to negative 2. Again, you multiply by negative 2, you get positive 4 here. Positive 4, negative 5, they add up to negative 1. So the remainder is negative 1 by the remainder theorem. Okay. So just to let you know what would be the result if you divided this by x plus 2. The result with the first one times what? If this is x to the power of 4, you are dividing by the first degree polynomial. So you bring the degree down by 1. So this is minus 1 x cubed. So in other words, if you divide this by x plus 2, what do you get? You get minus x squared. This is this one. Then minus 2x cubed, I'm sorry. Then 2x squared. Then minus x. Then minus 2. Then let's say plus, and then minus 1 over x plus 2. So again, the idea is this. These are the coefficients of the quotient, and the degree, this is 4, goes down to 3 and then move on. That's the meaning. Decide whether the given number is a zero of the polynomial. You can do it by synthetic division. You can do it by remainder theorem as far as the synthetic division is concerned. This one is 1 negative. And look, nothing is missing. The degree is 3 and then 2 and then 1 and 0. The constant has a degree 0. So you are going to say 1, negative 4, positive 9, minus 10. And you're dividing, it says 2. So that means they're dividing by x minus 2. So you put the 2, okay, and you go through the process. See, you drop the 1, times 2 is 2, 2 and negative 4 is negative 2. Negative 2 times 2 is negative 4 and 9 is 5. 5 times negative 2, 5 times positive 2 is 10, 10 and negative 10, they add up to 0. Because this is 0, yes, r equals 0, x equals 2 is a 0 of p, or you can evaluate p of 2, and I leave it for you to try it. If you plug in 2 here, 2 cubed minus 4 times 2 squared plus 9 times 2 minus 10 must become 0. For this one, we're going to put 3 halves, negative 1, 3 halves, and I don't see a constant. Then we must put a 0. And then negative 2, that means we are dividing by x plus 2, okay? And so you drop the first one, 3 halves, you multiply it by negative 2, you get negative 3, and negative 1 is negative 4, times negative 2 is 8, and 3 halves, 19 halves, times negative 2, you get 19, negative 19, and 0 is negative 19. So this is the remainder. So this is not a 0 of p. So r is not 0. It doesn't matter what it is. As long as it's not 0, that means x plus 2. This one is not divisible by x plus 2. X plus 2 is not a factor of p of x. You can evaluate it at negative 2 and you get the same answer. The rational zero theorem. If f of x equals a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 all the way to a sub 0, where a sub n is not equal to 0, is a polynomial with integer coefficients And if P over Q in lowest term is a rational zero of f of x, then P is a factor of the constant term a sub zero of f of x, and Q is a factor of the leading coefficient a sub n of f of x. In other words, if we are looking to find possible rational zeros in the form of a rational number P over Q, P would be factors of the constant a sub zero. Q would be the factors of the leading term a sub n. Okay, everybody? That's the idea. Number of zeros theorem. A function defined by a polynomial of degree n has at most n distinct unique complex zeros. Remember, a plus bi. That's the concept of a complex. Complex numbers are real numbers and imaginary numbers, the combination of the two, the union of the two. Descartes' rule of sign: determine the number positive and negative zeros. Let f of x be the above polynomial function with terms in descending powers of x. This is extremely important because if it's not in descending power, you just have to make it so. Okay, you put it in descending power. So that's extremely important, everybody, and then it works. A, the number of positive real zeros either equals the number of variation in sign occurring in the coefficients of P of x, or is less than the number of variations by a positive even integer. The number of negative real zeros either equals the number of variation in sign occurring in the coefficients of P of minus x, or is less than the number of variation by a positive even integer. What do we mean by that? I'll show you with a help of example. It's very straightforward. These theorems, we make some sense out of it shortly. Example 5, use the rational zeros theorem to list the potential rational zeros. That means not necessarily they are the zeros. Those are the possibilities of a polynomial function. F of x is 3x cubed plus 8x squared minus 7x minus 12. According to the rational zero theorem, notice that, first of all, this is degree 3, and therefore maximum we have 3 real zeros. Okay. So there are maximum 3 zeros. Not necessarily real, but rather 3 zeros. It's really a complex zero, I would say. So 3 zeros. Now, according to rational zero theorem, P is factors of a sub 0. This is the constant a sub 0. This is a sub n, or more precisely a sub 3, because not because it's equal to 3, because the exponent is 3. So according to the rational zero theorem, factors of negative 12 over factors of 3. Those are possible rational zeros. This is what rational zero says. So you write all possible factors of this number is plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 12. I hope everybody is comfortable with what I just said. Whereas for 3, plus minus 1, plus minus 3. Okay, so P for the numerator, these are the possibilities, okay? You always have plus minus 1. Plus minus 2 because divisible by 2. Plus minus 3 divisible by 3. Plus minus 4, 12 or minus 12 divisible by 4. Plus minus 6 divisible by that. Always you have this number and the number itself, okay? Plus minus. For this one, plus minus 1, plus minus 3. So divide this by this. That's it. Now, see what we are going to get. If we divide this one by this one, we get 1. This one by this one, we get plus minus 1/3. Okay. This one by this one, we get plus minus 2. This one by this one, plus minus 2/3. This plus minus 3. This plus minus 1. We don't have to repeat it. We had it already. This one plus minus 4. This one plus minus 4/3. This one plus minus 6. This one plus minus 2. We've already had that. This one plus minus 12. And this one plus minus 4. We've had it. So I hope you can see from here how we go to here. Put all possible results. As you can see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 times 2. 18 possibilities. Again, what does rational zero tell us? It says if we happen to have a rational zero, must be among those numbers. That's all it says. But which one is the zero, they are not telling us. This theorem just tells us those are possible rational zeros. One more time. How do you find it? Find the constant and all of its factors. Find the leading coefficient, 3, and find all of its factors. Divide those by those, and those are the possible answers. Now, find the real zeros and write f of x in factored form. Okay? It has at most 3 zeros, real zeros or complex for that matter. Okay? Now, the methodology is you check, and you check with the factor theorem. You plug in 1, you plug in -1, +2, -2. Let's say you plug in 1. If you get 0, that means x minus 1 is a fact. Do you follow what I'm saying? And because this is of degree 3, you divide by it, the result is degree 2. And when you get to degree 2, you can do it by factoring or the quadratic formula. You don't have to continue. But if the degree is higher than 3, you may check. So you check 1, you check -1, 2, -2, 3, negative. You keep on checking and you get all the answers. But because this is degree 3, if one of them works, practically we are done. So let's look at factor theorem. If we plug in -1, everybody, again, I don't want to go through checking all of it, but the idea is that you have to plug in 1. And I hope you see that 1 gives you 3 plus 8, 11, minus 7, 1 minus 12 is minus 11. So 1 doesn't work. I hope you see that. And so if you plug in -1, what happens? This is -1 times 3 is -3. This is +1 times 8 is +8. This is +7 minus 12. So let's just write that. So because this is -1, we have -3. Because this is 1, we have +8. We have +7. We have -12. And I hope you see it's 0. We found one answer. This means the factor of x plus 1 is there. This polynomial can be divided by x plus 1 and give us the remainder 0. Because we found that, we are going to do synthetic division to find the result when we divide by it, which becomes a second degree polynomial or quadratic. So let's do that. And by now we've done synthetic division a lot, so we're going to quickly look at that. 3, you drop it, times -1, -3, and 8 is 5. Times -1, -5, and -7 is -12. Please understand, we're not changing sign, unlike long division, don't mix them up. -12 times -1, +12 and -12 is 0. That means this was degree 3, right? Now this one is 3x squared, degree 2, plus 5x minus 12. Therefore, this function is x plus 1 times 3x squared plus 5x minus 12. Now, what do you do with this one? If you want to continue with this, you can, everybody. Meaning you can try 2 and -2, 3 and -3, so on and so on, to see what works. But when you get to degree 2, you can either go by factoring or the quadratic formula. Because 3 is a prime number, it makes it easy. You have to go with x and 3x, right? And then 12 negative. You go with 1 and 12, one of them negative. 2 and 6, one of them negative. 3 and 4, one of them negative. So trial and error gives you that. Okay, everybody? So we get x plus 3 times 3x minus 4. So this is all the factored form. Now, we want to find all zeros. We said one of the zeros was -1, the other one is -3, and the last one is 4/3. So set it equal to 0. And we have -1 we had already found. This gives us -3. This gives you +4/3. As you can see, all of these rational numbers are among those numbers. Because if you happen to have a rational 0, must be among those and nowhere else. Use number of zeros theorem and Descartes' rule of signs to discuss real zeros of f of x. In other words, we want to see how many zeros we have and positive, negative, and so forth. First and foremost, this is in descending order. It has to be in descending order. And look at the leading term. Leading term has degree 7. So maximum number is 7. So maximum number for the zeros is 7. And that's the maximum number of complex zeros, or of course, for that matter, real zeros. So we have 7. Now, let's see what we can notice here. What I want you to notice is that this has a positive sign. This has a negative sign, positive sign, positive sign, negative sign, negative sign. And as you check, we are going from positive to negative, positive to positive to negative to negative. we are going to look at how many changes takes place here. From positive to negative, there is one. From negative to positive, that's the second one. Then from here to here, there is no change. Okay. And then from positive to negative, there's one more change. And from here to here, there's no change. So we have one, two, total of three changes. So the positive real zeros could be 3, or you go down by 2, maybe 1. We are going to evaluate f of minus x. So 3 times minus x to the power of 7 becomes minus 3x to the power of 7. Minus 4x to the power of 4 doesn't change because the degree is even. So minus x to the power of 4, this changes to minus 3x cubed. This doesn't change. This changes to plus x. This doesn't change. It's a constant. So what happens now? We notice a negative, negative, negative. Nothing is happening. But from here, there is a change. Here, no change. Here, there is a change. So we write the signs. And we say we have 1 and 2 changes. So we have 2 maximum, 2 negative values. And we write, for the positive real zeros, we ended up with 3. For the negative real zeros, we ended up with 2. So for the positive, we could have 3, maybe 1. For negative, we could have 2, maybe 0, because you have to go down by 2. So you subtract 2 from 3, you get 1. You subtract 2 from 2, you get 0. Those are possibilities. And by any chance, if you ask, okay, what about total of 7? We will discuss that later on. Total of 7 comes from the fact that we have 7 complex zeros. Determine the possible number of positive real zeros and negative real zeros for p of x equals x to the power of 4 minus 6x cubed plus 8x squared plus 2x minus 1. So the very first thing we do, we look at it just the way it is and make sure you understand this is positive, okay? So there is a change from positive to negative. There's another change from negative to positive. No change, positive to positive. And another change, so we have total of 3 changes. Therefore, the function has either 3 or 3 minus 2 equals 1 positive real zeros. So pretty straightforward, everybody. Let's evaluate p of minus x. When we do that, this becomes itself, x to the power of 4. This becomes minus x cubed with the negative becomes positive 6x cubed. This is itself x squared, so 8x squared. This is minus 2x, this is minus. Positive to positive to positive, no change. Positive to negative. So we find a change here, and then negative to negative, nothing happens. So there is one change. Since there is only one variation in sign, P of X has only one negative real root. Definitely one. Example 8, find the real zeros of a polynomial function. Write f of x equals 2x to the power 4 plus 13x cubed plus 29x cubed plus 27x plus 9 in factored. So we want to find the zeros and write them in factored form. We notice the degree is 4. We have at most 4 real zeros. And according to the factored rational zero theorem, factors of the constant 9 over the factors of the leading coefficient 2. Okay, rational zero theorem. The constant is 9. The leading coefficient is 2. And as you can see, this one is just plus minus 1, plus minus 2. This one is plus minus 1. Let's just write the possibilities for the top. This would be plus minus 1, plus minus 3, plus minus 9, and no more. This would be plus minus 1, plus minus 2 only. So this would be plus minus 1. This would be plus minus 3. This would be plus minus 9. This would be plus minus 1/2. This is plus minus 3/2. This is plus minus 9/2. So I hope everybody's okay with those. So that means those are the only possible rational zeros. And again, you have to try those to see which one works. Factor theorem is used because it's faster than the synthetic division. First, we're going to figure out what works. If you look at negative 1, you have 2 times negative 1 to the power 4 plus 13 minus 1 cubed plus 29 minus 1 squared plus 27 times negative 1 plus 9. Let's see what we get here. So this is 1, we get 2. This is negative 1, we get minus 13. This is 1, we get 29 minus 27 plus 9. 2 minus 13 plus 29 minus 27 plus 9. They add up to 0. So right away, this means x plus 1. X plus 1 is a fact. Let's do synthetic division and find now what? This is degree 4. When we do the synthetic division, we find the result with degree 3. So let's do the synthetic divisions. Again, we're going to go through it fairly fast. We're going to put 2, 13, 29, 27, 9, and nothing is missing. Take a look. Nothing is missing because degree 4, degree 3, degree 2, degree 1, and degree 0 are constant. All of them are there. So you bring the 2 down. You multiply it by negative 1. You get negative 2 and 13 is 11. You multiply it by negative 1. Negative 11 and 29 is 18. You multiply it by negative 1. Negative 18 and 27 is 9. You multiply it by negative 1. Negative 9 and 9 is 0. What does that mean? The result is, so this one is 2. Remember, this is a exponent 4. Now this is 2 exponent 3. 2x cubed plus 11 x squared plus 18, x, and this is a constant 9. So this is the result. Now, because this is degree 3, we have to continue, either check more, and there's no other choice. You have to check more. To check more, what is important for you to remember? You have to do it with -1 again, because it may be of multiplicity 2. So that's why you are going to check with -1 again before you check any other number. So one more time. If is divisible by x plus 1, if x plus 1 is a factor, it may be a factor of multiplicity 2. That means x plus 1 squared. So you have to do the -1 one more time. We bring the 2 down, multiplied by -1, -2, and 11 is 9, multiplied by -1, -9, and 18 is positive 9, -1 gives you -9, and 9 is 0, and it checks, which means it's x plus 1 squared times. Now, this is degree 3, it goes down to degree 2. This is 2x squared, this is 9x, this is 9. So 2x squared plus 9x plus 9, this is degree 2. And I hope you realize, because we have degree 2, we can continue with the process, but it's easier to either factor, if we can, or use the quadratic formula. Either way is fine, okay? So when you get to second degree, that may be the way to go. So this one, again, it's fairly easy because 2 is a prime number, everybody. So this is x, and then 2x and 9. You have no choice but to go with 1 and 9, or 3 and 3. 3 and 3 will do the job. That means x is either -1, -3, or -3 halves if you set it equal to 0. Okay, this has a multiplicity 2. And if for any reason somebody asks, what is the solution to this equation? If you set this equal to 0, you get to the same answer. Please, the answer to this question is also the same thing. Bounds on zeros theorem. Let P of x define a polynomial function of degree n larger than or equal to 1 with real coefficients and with a positive leading coefficient. If P of x is divided synthetically by x minus c, and if c is larger than 0 and all numbers in the bottom row of the synthetic division are non-negative, then P of x has no 0 greater than c. C is the upper bound. If c is less than 0, and the numbers in the bottom row of the synthetic division alternate in sign, by the way, with 0 considered positive or negative as needed, then P of x has no 0 less than c. C is the lower bound. What do we mean by that? Example. Show that the real zeros of P of x equals 2x to the power of 4 minus 5x cubed plus 3x plus 1 has no real 0 that is greater than number 3. So we do synthetic division with respect to number 3. Notice what happens. We are going to go through the process. We put 2, -5, x squared is missing. We put 0, 3, and 1. We divide by We put 3 here, which means we are dividing by x minus 3. That's the minimum. You drop the 2, you multiply it by 3, you get 6. With negative 5, you get positive 1. Multiply by 3, you get 3. With 0, you get 3. Multiplied by 3, we get 9. 9 and 3 is 12. 12 times 3 is 36. With 1 is 37. Look at these numbers. If c is larger than 0, so number 3 is larger than 0. And all numbers in the bottom row of the synthetic division are non-negative. Look at it. All of them are non-negative. That means even 0 is okay. As you can see, all of them are positive. That means no real 0 greater than 3. Now, one might say, okay, what is the advantage of that? When you do the rational zero theorem and you have many, many numbers to check, and it happened to be known that 3 is the upper bound, any number larger than 3, you don't have to check. On the other hand, if we check with negative 1, that means we are going to put the same numbers. Instead of 3, we want to put negative 1. Notice what happens. You drop the 2, you multiply it by negative 1, negative 2, and negative 5. They add up to negative 7. Times negative 1, positive 7, and 0 is 7. Times negative 1, negative 7, and 3 is negative 4. Times negative 1, 4, and 1 is 5. So, what's happening with the sign? If c is less than 0, this is less than 0, negative. And the numbers in the bottom of the synthetic division alternate. So this is positive, negative, positive, negative, positive. They alternate, and 0 is whatever you want it to be. Then P of x has no 0 less than c. So this is the lower bound. The numbers alternate in sign, no 0 less than negative 1. So again, what is the advantage of that? You have many, according to the rational zero theorem, you may have many zeros to check. If this is your upper bound, you're not going to check any number larger than 3. If this is your lower bound, you're not going to check anything less than negative 1. So it's pretty straightforward. Find the real zeros of a polynomial function. So write f of x equals 2x cubed plus 11x squared minus 7x minus 6 in factored form. The degree or n is 3, so we have at most 3 real zeros. According to rational zero theorem, we're going to look at factors of the constant negative 6 over the factors of a sub n, the leading coefficient 2. So for negative 6, let's just write each one. For negative 6, we have plus minus 1, plus minus 2, plus minus 3, plus minus 6. For 2, we have just plus minus 1, plus minus 2. So if you divide all of them by plus minus 1, you have all of the above. And then if you divide them by 2, you have plus minus 1/2. This is the same as 1, plus minus 3/2. And this is the same as plus minus 3. So these are possible rational zeros. And you have to check. And You normally go with the easy ones, either 1 or -1. Just for the sake of argument, let's do something different. Let's try -6. And again, class, you really have to start with the easy ones. Check 1, check -1, 2, -2, so on and so forth, and you get to the answer pretty fast. So if you plug in -6, 2 times -6x cubed plus 11 times -6x squared minus 7 times -6 minus 6, and you get to 0. If you work it out, so for the sake of argument, this is a negative 36, and this is positive 36. And you work it out, you end up with 0. That means -6 is a 0. That means we can do a synthetic division to find a second degree polynomial or a quadratic polynomial. Synthetic division. We're going to put 2, 11, -7, and -6 here. We're going to, and we put this one -6 here. So 2 drops, multiplied by -6, you get -12. Add them up, you get -1. Multiplied, you get 6, and -7 is -1. Multiplied, you get 6, and -6 here. And that means when you divide this one by x plus 6, so when we have -6 here, x, this means x plus 6 is a factor, okay? Then what is remaining when you divide? This is degree 3, so this would go to down by 1. 2x squared minus x minus 1. 2x squared minus x minus 1. And of course, this is an easy factoring because 2 is 1 and 2. So, by the way, the terminology, this one is called the depressed equation of f of x, if anybody is interested in the terminology. And factoring will result in 2x plus 1 and x minus 1. Because we are interested in finding zeros, this gives us -6. Set it equal to 0. This gives you -1/2. This gives you +1. Use the theorem for bounds on zeros. Given f of x equals 2x cubed plus 11x squared minus 7x minus 6. Find integer upper and lower bounds on the zeros. That's the same function as the previous page. We have already done that. Recall we came up with this, right, class? Recall we have this. For upper bound, start with the smallest positive integer and move up. In other words, check +1, check +2, check +3, and so forth. If you check +1 and it works out, that's your upper bound. That means you don't have to worry about +2, 3, 6, which makes it really nice. That's why if you want to check the upper bound, you start with the smallest one. You don't start with the largest one because obviously if the largest one is the bound, you have to check the rest of them anyways. But if you find any of the smaller one, then you're in good shape. So when we check with 1, everybody, notice what we get. So first of all, 2, 11 minus 7 minus 6. We are checking with 1. So we are dropping 2 times 1 is 2. With 11 is 13 times 1 is 13. With -7 is 6 times 1 is 6 with negative 6 is 0. As you recall, this was a 0 of the function anyways, or if you look at f of 1. Okay, if you plug in 1, you will get 0, which actually we got lucky. The first shot, we got actually a 0 of that. Not only that, positive, 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 and remember 0, as long as it's non-negative, okay? That means 1 was the upper bound anyways. So what is the beauty of that? You don't have to worry about 2 or 3 or 6, okay? That's the idea. Now, for the lower bound, start with the largest negative integer, the most negative one, and then move down, and then after. So you go with -6, -3, -2, and so forth. That's the reverse process. Now, we can look at the summary of that because this takes a little bit of a time. We looked at number 1, and because the coefficients are what you have, including the remainder, it's all negative. Number 1 is the upper bound. I can do the rest of them, okay? And -7, this is the one, the alternates. Notice positive to negative, negative to positive, positive to negative, and that means the lower bound. So according to this, upper bound is 1, lower bound is -7. That means you really have to check -6. That's why it ended up being 0. And if you look at this one, positive, negative, negative, it doesn't alternate. You don't know that. But anyways, you have to continue checking. So that's the idea behind the upper and lower bound. Example 2. Consider the polynomial function p of x equals 2x cubed plus 5x squared minus x minus 6. Show by synthetic division that -2, -3 halves, and 1 are zeros of p, and write p of x in factored form. You can do it by factor theorem. They want us to do it by synthetic division. We do it pretty fast. If you put those numbers in order: 2, 5, -1, -6, and there is no term missing. So with -2, you drop the 2, times -2, -4, and 5 is 1, times -2, -2, and -1 is -3, times -2, 6 is 0. So that is a proof for -2. For -2, again, I want to make sure we understand that. For -2, it means the factor of x plus 2, okay? Let's check the next one. So p of -2 is 0, if you go with that. With the next number, which is -3 halves, again, 2. Now, if you divide this one, since you know this is the case, you can divide this one by -3 halves, okay? So 2, 1, -3, you drop the 2, you multiply by -3 halves, -3 and 1 is -2, times -3 halves is +3, they add up to 0. So that means p of -3 halves is 0. That means the factor is x plus 3 halves, okay, everybody? And now you can use this and divide by the next one. So 1 means x minus 1. So 2, you drop it, okay? Times 1 is 2, 2 and -2 is 0. That means p of 1 must be 0. And that means x minus 1 must be a factor. Now, here's the answer. I want to make sure we understand what happens. So according to the factors, we're going to write x plus 2, x plus 3 has x minus 1. I want to discuss this. This 2 is the constant factor. If you go back here, because the leading coefficient was 2, this wouldn't indicate that. If it were 5, you would have to put that here. So it's important to see what's happening and why you have to put that. If you don't put that, it's not going to work out. Graph P in a suitable viewing window and locate the x-intercepts. You can use a calculator, and P of x is the given function 2x cubed plus 5x squared minus x minus 6. With the TI, you can go with calc, second trace 0, left bound pick a value, right bound pick a value, guess enter, and it gives you those. You can try it. Solve the polynomial equation. So basically set the factored, set this one equal to 0, which means you set the factored form equal to 0. Okay, if you set the factored form equal to 0, x is negative 2 here, x is negative 3 halves here, and x equals positive 1. Because the zeros of P are solutions of P of x equals 0, the solution set is braces, negative 2, negative 3 halves, 1, close braces.